The most fundamental question you can ask about a robot is, where is it? The answer to this question is the robot's configuration, which is a specification of the positions of all the points of the robot. In this book, robots are constructed of rigid bodies, like this one. We often call these rigid bodies links. These links are connected together by joints, like this Revolute joint of my Tinker Toy robot. Since the links are rigid and have a constant shape, we typically only need a few numbers to represent the configuration of a robot, compared to trying to represent the configuration of this pillow, which can be deformed in a wide variety of ways. Some robots, called soft robots, are like this pillow, but we don't cover soft bodies in this book. So the configuration of a robot is a representation of the positions of all the points of the robot. The configuration space, which we often call the C space for short, is the space of all configurations of the robot. The number of degrees of freedom is the dimension of the C space, or the minimum number of real numbers you need to represent the configuration. As an example, this two-joint Tinker Toy robot has 2 degrees of freedom given by the angles of the 2 joints. I can visualize the angle of joint 2 as a point on a circle, and the angle of joint 1 as a point on another circle. To visualize the full C space, let's rotate the circle for joint 1 to be perpendicular to the circle for joint 2. At each angle of joint 1, there is a circle of possible joint angles for joint 2, so I can replicate the joint 2 circle at every angle of joint 1. Therefore, the C space of the 2-joint robot can be visualized as the 2-dimensional surface of a torus. Now, for every configuration of the robot, there is a unique point on the torus, and for every point on the torus, there's a unique configuration of the robot. As I mentioned earlier, the dimension of a robot's C space is the number of degrees of freedom. Since a robot consists of rigid bodies, the number of degrees of freedom of a robot depends on the number of degrees of freedom of a rigid body. A rigid body in 3-dimensional space has 6 degrees of freedom, but how do we determine that? First, let's choose the position of one point on the body. Let's call that point A. The XYZ coordinates of point A are 3 numbers. Next, we can choose the XYZ coordinates of a second point, B. But because this is a rigid body, we can't choose the 3 coordinates arbitrarily. B's constant distance to point A places one constraint on its location. The point B has to be somewhere on the surface of a sphere centered at A, and we only need 2 numbers to represent a point on a sphere, like latitude and longitude. Now that we've fixed points A and B, there are 2 constraints on point C. It has to be on the circle at the intersection of spheres centered at A and B. We only need 1 number to specify a point on a circle. Once we've fixed the location of points A, B, and C, provided they are not all on the same line, the body is fixed in space. Therefore, a rigid body has 6 degrees of freedom. 3 to specify the location of point A, 2 to specify point B, and 1 to specify point C. To summarize, let's count for each point on the body the number of coordinates, the number of constraints on those coordinates, and therefore the number of real freedoms in choosing each point. Point A has 3 coordinates and no constraints in how we choose them. Point B has 3 coordinates, but they're subject to 1 constraint, so we only have 2 real freedoms. Point C has 3 coordinates, but they're subject to 2 constraints, so there is only 1 real freedom. All other points have 3 coordinates, but are subject to 3 independent constraints, so there are no further freedoms. Thus, a rigid body in space has 6 total degrees of freedom, 3 of which are linear, or XYZ, and 3 of which are angles, sometimes called roll, pitch, and yaw. We could use the same process to learn that a rigid body in a 2-dimensional plane has 3 degrees of freedom, 2 of which are linear and 1 of which is an angle. We could even study a rigid body in 4-dimensional space and learn that it has 10 degrees of freedom, 4 of which are linear and 6 of which are angles. We can summarize what we've learned in this video with the following general rule, which holds for any system, not just rigid bodies. The dimension of the C space, or the number of degrees of freedom, equals the sum of the freedoms of the points minus the number of independent constraints acting on those points. Since our robots are made of rigid bodies, we can express the number of degrees of freedom more simply as the sum of the freedoms of the bodies minus the number of independent constraints acting on the bodies. As an example, we can take the 6 degree of freedom spatial body and turn it into a 3 degree of freedom planar body by adding 3 constraints that the z coordinates of points A, B, and C are all equal to 0. In the next video, we will use what we've learned to understand the number of degrees of freedom of a general mechanism.